Okay, so third section on chapter 4, which is about moments, and this is about equilibrium. Now all we need to remember, if something is in equilibrium, so not something, a system. So if a system is in equilibrium, then the forces are balanced. The forces are balanced, and the sum of the moments is 0. The sum of the moments is 0. So we could probably summarize that in a diagram. So if you have any upward forces, they will equal any downward forces. If you have any clockwise moments, they will equal any anti-clockwise moments. So we're looking for those two things. We're looking to see that the moments are balanced and the forces are balanced. Now, one thing we probably need to look out for is questions like this. Something is on supports, so you might have the mass of the plank or whatever going down. It may be uniform or non-uniform, which means that you may or may not be able to put its mass in the center. But what we need to remember is there's going to be a normal reaction from these pivots. Yeah, there's going to be a normal reaction from these pivots, which we need to consider. And actually, whenever you've got, let's say we've got like the floor down here, and this is some sort of wall, and let's say we've got like a ladder leaning on the wall like that, this would have like a normal reaction here and a normal reaction here. You always have this perpendicular force where an object is in contact with a surface. Yeah, so just be aware of that. Right, so question like this, I always start to draw on any forces that we have. So we've got the full length of the rod. We've got, it tells us that it's uniform. That means that the weight of 20. So notice we've got the weight, not the mass. So we don't need to multiply that by G. We've got the actual weight. That is going to be in the very center of the rod because it's uniform. So we're going to have 20 newtons going down like that. And because the rod is 3 meters long, this will be a distance of 1.5 meters. Because it's uniform, we can do that. We also need to put in the reactions. Now we don't know the reactions, and there's nothing to say that the reactions are the same. Do not assume they are the same unless the question says they're the same or one is twice the other. So we're going to call this reaction, well, it's point A, so we'll call this reaction A, R for reaction, and this reaction C because that's the point C. Okay, so we've got everything that we need on there. It says that it's resting on the support, so it's not moving, it's not tilting anywhere, which means that the forces are balanced and the moments are balanced. So let's start with the forces. And if I look at the forces pointing up, I have RA plus RB. They will equal the forces pointing down, which is 20. Okay, so I've got equation number 1. RA plus RB is 20. Okay, let's look at the moments. Okay, now when we take moments, we need to pick a pivot point. There's nothing on here marked as a pivot point. Now I could pick the pivot point wherever I like. I could make it here. I could make it anywhere along the rod. I could make it here, or I could make it here. Now we want to make the working as easy as possible. Now if I made the pivot point here, then I'll have a force of RA times that distance. I'll have a force of RC times that distance. I would end up writing the equation that has both RA and RC in it. And I've already got an equation with RA, spot the mistake, and RC in it here. And I don't really want another one. It would be nice to have an equation which just has RA equals something or RC equals something, and then I've got RA or RC straight away, and then I can plug that straight into the first equation. So I'm going to choose a pivot point. Now I would suggest either you choose point A as your pivot, because if you do that, then the only reaction that's going to appear in your equation is going to be RC, because the distance from here to this force is 0, so it won't appear in the moments equation. Or I could pick C as the pivot point, and then this won't appear in my moment equation, because I'll just have that distance times that force and this distance times that force. I'm going to choose point A as my pivot point, so I'm going to draw it like this. This is A, and now I'm going to put in the forces and draw my moments diagram. So I've got 1.5 times 20. Then I need the distance from A to C. So that's a force of RC, and from the question I can see that this is a measurement of 2 meters. Right, so now I can write my moments equation. I'll put on here the clockwise. So this is trying to rotate it that way. That's trying to rotate it that way. So that means that this is going to be a plus because it's clockwise. This one's going to be a negative because it's anti-clockwise. And my moments equation is going to be 2 times RC, or negative 2 times RC. Let's start with the positive one first. So we'll have 1.5 times 20, or 20 times 1.5. Now what did we say? Actually, it's all in equilibrium, it's not movement. So the clockwise and anti-clockwise will be equal. Or you could say, right, that the positive one, so you could write it this way instead, it's the same thing. And then the negative one is 0. Yeah, the sum of the moments is 0. Yeah, so up here we've got that the forces are equal, the upward forces, which are these two, that one and that one, equal the downward force. And here we've basically got that the clockwise equals the anti-clockwise. So whichever way I write that equation, I will have from there that 30 equals 2RC, which basically means that RC equals 15. So that's the reaction at C. Okay, now if I substitute that back into there, nice and easy, I can see that RA must equal 5. So there we go. So we've got the reactions at both of those supports, because we're able to write 2 equations, one for the forces, one for the moments. Okay, so this question here, we're going to do start by drawing on the forces. So I'll put, well, let's read it first. So it's a uniform beam of mass 40 kg. So in the very center of it, I'm going to have a weight of 40 g. Okay, now it's 5 meters long, which means that this distance here is 2.5 meters because it's uniform. We've got a man standing on the rod at a point E, and we don't know how far along he's standing on that rod. Let's put his mass in. So let's put 80g here, and let's call his distance from the we need to find a distance from A to where he's standing. So let's call the distance from A to where he's standing x. So we want to find x. So x is going to be that distance there that we need to find. Important bit of information here about the reactions. It says that the reaction at D is twice the magnitude of the reaction at C. So we can use the same letter. The reaction at D is twice that at C. So let's call the reaction at C, let's just call that R. And the reaction at D is double that. So this is going to be 2R. Okay, so we've got all of our forces, information, distances on the diagram. So just like before, we're going to balance the forces and we're going to balance the moments. So if I start with the forces, so what have I got going up? R plus 2R, that must be balanced with what's going down, 40g plus 80g. Okay, so that means that 3R equals 120g, which means that R is 40g. Now that's not our final answer, but what that's going to do is that's going to now allow us to do the moments using numbers rather than using R's. So I'm going to write on here that this is 40g because I've just worked that out, and this one then is 80g because it's 2R. Right, so just like before, we need to pick a pivot point. Now here's a hint, my little Heinz hint. Now it says find the distance AE. Okay, so since we're trying to find the distance from A to E, let's make A our pivot point. Let's make that the pivot, because then we can do a distance times a force. If you pick other points as your pivot point, yes, you will get the answer, but you're making things more difficult. Okay, so my Heinz is, if you need to find a distance from a point, okay, make that point your pivot. Make that point your pivot. So I'm going to make this point here my pivot. Okay, so what I'm going to do is I'm going to draw a moments diagram, because there's lots going on over here and I probably just want to simplify it a bit, so to make my equations a bit easier to work out. So here's my point A, there's my pivot. So that's 40g. Now from the original question I can see that's a distance of 1 meter. We go across a bit further, so these are all perpendicular by the way. I've got another 40g here, and that distance is 2.5 meters from there to there. Then I've got the distance to the man, 80g, and use a different color. All of this distance here from there to there is x, and then the last one is the distance to this reaction here, which is 80g, and the distance from the end to that pivot, well, if the whole thing is 5, and that's 1. So the distance from A to the pivot must be 4. Let's use a different colour and put 4 meters from there to there. Right, okay. Let's put which ones are clockwise and anti-clockwise. So that's trying to pivot around that way. That's trying to pivot around that way. That's pivoting that way. That's pivoting that way. Right, so that means that this one and this one equal this one and this one. There's my second equation. Okay, so that's going to be 1 times 40g, don't forget the g, plus 4 times 80g equals 2.5 times 40g plus x times 80g. Yeah, so our clockwise equals our anti-clockwise. Right, let's simplify that a bit. So if I've got 40g plus basically 4 times 80, 320g. So altogether on the left hand side I will have 360g equals 2.5 times 40 is going to be 100g plus x times 80. So we'll take away 100g from both sides, so we'll have 260g equals x times 80, 80g, and if we do 260g divided by 80g, it's worth you leaving the g's in, because what happens is they, like those types of things, tend to cancel out. So rather than work out 40 times 9.8 or 80 times 9.8, if you leave in terms of g, they cancel out. That will give us x equals 3.25 meters, just enough space to squeeze in the answer there. X is 3.25 meters. Yeah, so by choosing the right place for the pivot point, we make our working easier. Yeah, so always think about that. Don't just pick any old place. Choose somewhere that is going to make your working easier. Okay, so this question here, it says that this uniform rod is hinged at point P. So P is like the pivot point, and there's a hinge. Now, whenever you get any question that says that there's a hinge somewhere, so there is one down here, there is actually a horizontal and vertical part to the reaction. Okay, now you're going to see in a moment, if we're clever about our working, that need not bother us, but it's important to note. So if a rod or similar is hinged at a point, there will be a horizontal and vertical component or parts to the reaction. Okay, now in normal circumstances we'd probably need to work out what that is, but if we look at the question, we think carefully, then we can actually eliminate that, and the way that we can eliminate it is by taking moments at P. If we take moments at P, then we need not concern ourselves with either part of that normal reaction. And actually sometimes with these questions you don't even need to look at the forces. You might actually be able to solve this just by taking moments, and I think this is one of those questions. So whenever I get a question like this, I would always take moments first. I know in some of the other examples I've done the forces first, then the moments, but there's only one unknown really. If we take moments at P, the only unknown is going to be F. If we take moments from a different point, we choose a different pivot point, then we're going to have to look at the vertical and horizontal component of the reaction at P, and we really don't want to get into that. So what I'm going to do, if P is my pivot point down here, then I'm looking at a force times the distance. So I've got a force of F. The rod is 3 meters, so I've got that force and that distance. But then I've also got this 8G going down here, 8G, and this is going to be the perpendicular distance. This bit here, that's the bit I'm interested in. Now, let's zoom in on what's going on here. So this is 50 degrees here. I want to find out how long this is. That's going to be what I multiply the 8G by. Now what's missing? It's a uniform rod. Right, now if it's a uniform rod, that means that this mass is acting at the center of the rod, which means that this distance here is half of the 3 meters, 1.5. So let's put that in. So 1.5 meters. Now, because the side I'm trying to find is adjacent to the angle, this side here is going to be 1.5 cos 50. I think it's the first time we've used cos in a moments question. It's normally been sine. So this is going to be 1.5 cos 50. Right, now that's all we need. We've got a moment going that way, which is going to be negative. We'll take that as negative because it's anti-clockwise. A moment going this way, which is clockwise. We'll take that as positive. The whole thing is in equilibrium. It says it in the question. So that means that the moments are balanced. And notice I haven't had to consider any forces at all, and not even bothered with the forces going on at the hinge, because we've got everything we need. So the moments are balanced. So 3F equals 8G times by 1.5 cos 50, which means that F equals, well, basically that divided by 3. Okay, and we can just type that in on our calculator as I see it. So fraction button, 8 times 9.8 times 1.5 cos 50. That looks like a 30. Let me change that. Cos 50. And then that's all being divided by 3. And I get 25.1972743. So we'll go for 3 significant figures. So we'll go 25.2 newtons. That's the size of that force. Okay, so even though this is in the examples where we were looking at forces and moments, I was able to solve this question just by moments because there was only one unknown. Unlike in the previous question, there were 2 unknowns, so we can get away with one equation, and we avoided having to sort of deal with like these reactions here. Yeah, maybe later on we might need to, but you know, we can leave that to one side by taking moments at that point, and those forces do not occur in our moments equation. Okay, so exercise 4C, which starts on page 78, and it's pages 78 to 80. So you should now be able to do that exercise.